So, hello and welcome to this week's video for Python 101. This week we're doing some binary conversions. We're going to be doing it using a couple different methods, and since this is kind of a little bit more of an abstract kind of conceptual problem this week, I'm going to do a little bit of drawing here in order to just kind of illustrate the two different algorithms that we're going to be building, or really like implementations of algorithms, or however you want to say it. So first off, obviously binary is base 2, using only the first two symbols, which are 0. Oh, whoops, I don't want it to convert. Hold on, 1 second. I don't know why it's doing that. I see, I had the wrong tool. 0 and 1, right? Which is as opposed to, the number system that we usually use as human beings. It makes the most sense to us that we grew up with, which is base 10. So we have 10 characters. And then we use different combinations of these characters to denote a number's value. So like, for example, let's use the number, let's just do something totally random, 325. Sure, why not? So this number denotes how many 10s there are, right? Which is, or sorry, how many, excuse me, big misspeak there. How many 1s there are, which is 10 to the 0, because we always start at 0. And then this is the amount of 10 to the first. So that's the tens count, excuse me. Right here is the tens count, of course. And then hundreds, which is 10 to the 2. And if we had a longer number, this would continue on this way. We'd do, 10 to the 3 and so on and so forth. So each digit in the number represents, a higher order of tens, basically, that we're adding. And, we don't think about this every day, but these are conversions that we do every day without even thinking about it. Now, binary, like I said, you only have two symbols, right? So basically, what you're going to do in order to convey information or represent numbers using only two symbols is you're going to use, instead of powers of 10, which is how many symbols we have here, right? We have 10 symbols here. Weird. Little slash. We're going to use powers of 2 because that's how many we have here, right? We got two characters, and we got 10 characters here, right? So we'll start with 2 to the 0, so that's still the amount of 1s that you're going to have. And then 2 to the first, 2 to the second, 2 to the third, and so on. So let's just generate a random string of binary here, and then so this is 2 to 4, this is 2 to 5, this is 2 to 6. So now we can work backwards from here. So we have 0 1s, we have a 2, we skip the 4s, we have an 8, we have a 16, skip the 32s, and we have a 64. So we add these up. We get 10 plus 16 is 26, plus 64 equals 90. So this is 90 in binary. Let me just double check that real quick. I'll actually use my converter to check my conversion. That's on my other monitor, so you'll see that in a minute. So 1011, 010, 7 bits. That's our answer. Correct. And of course, bits are binary digits. Whoa, hello. Digits. And then, you and then you go and then you get bits, binary digits, right? I mean, I left both eyes, but you get the idea. So there's 7 bits. And yeah, this is how we convert to binary, or this is what binary is, excuse me. So to explain how we're going to convert numbers to binary mathematically, we have two different methods here. which I will illustrate. So first off, we have our, this is going to be called our powers of 2 method. And it's called this because we're going to basically, basically we're going to do what I just did, like quickly by counting those up, but we're going to do it in a more formal way. So what we're going to do is we're going to take our number. So let's make another one, 153, let's say, right? And we're going to make a table, and we're going to make, we're going to fill one side of the table with values, powers of 2 up to when it gets greater than our given value, right? So we'll call this, actually, we don't need to give it a name. That's just going to make things more complicated. So anyway, so we're going to get 1, 2, 4, 8, 16, 32, 64, 128, and then the next power would be 256, which is greater than this, so we could just count that out because we know we're not going to have any counts of that. Now we work backwards. We go, is 128, able to go into this? Yes. So we mark it 1, and we subtract 128 from what we have. We get, whoops. Stupid. It's doing addition, my bad. Yoo-hoo. Let's try that again. Wow, God. 4, 13. Okay, so we get 25. Just double check my math just to make sure, because it's been a while since I've done baby subtraction like this, to be honest. I usually just punch stuff in, which maybe is a fault of mine. But I don't think computers are going anywhere. But anyway, yeah, I was right. So look at that. The oldest computer, my brain. Well, not my brain, but the brain. Of course, my brain's only 23 years old, but I digress. My brain worked, is my point. So 25 is what we're left over. So 25, 64, too much. 32, too much. 16, yes, we could take one of those. We take a 16 away. I don't need to do any math there. It's just a 9. Yes, 8 will go into that. We're left with 1. So we have 0 4s, 0 2s, and we have a 1. So now we go backwards. Now this is very important to note. You start with this, and then you write right to left. So you go 1, 0, 0. I'm gonna write an arrow here. And like connect that. I don't know if that illustrates it well, but we're going up this way. So 1 0 0 1 1 0 0 1 1 0 0 1 1 0 0 1 should be 153. Let's use our converter to check, and it's 1. Yep, that is correct. And this is 8 bits. So we're good. All right. So that's the powers of 2 method. Now, this method seems somewhat efficient for small numbers, because it is. But the thing is, obviously, the first and most apparent thing is you have to make a table, right? Which is obviously just like more, it's a step of, it adds a step of work that could possibly, be taken out, which is what we're going to get to later. Like you don't necessarily have to build a table in order to do conversions, right? So there's that. And then there's also the fact that you have to do subtraction, which is kind of harder to keep track of than other, operations. So how can we do this more efficiently? Let's take a look. So we're going to, how do I just clear the page? Whatever. Let's use my eraser. So that's our powers of 2 method. We use a table. Fill the table up into the value that's greater than the one that we started with, and then we work backwards from there. Now the other method is the modulo method. Now modulo is this operator here, which basically says this means the remainder. Whoa, that was horribly ugly. Remainder of of division. So for example, 2 modulo 2 is 0. There's no remainder. It divides evenly into excuse me, I forgot to say that. 2 modulo 2 is 0 because there's no remainder. 1 evenly goes into 2 times, right? But let's say 3 mod 2, that would give us 1 because we have, technically the answer is 1.5, but if we're doing integer division, then we have 1 with a remainder of 1. So that's what our modulo does. So we're going to use this because essentially what you can use modulo for in a very slick way is to convert values to binary without having to make any kind of table or even really keep track of the work that you're doing. It will just naturally work out. So here's what we're going to do. Let's choose a big number just for the sake of it. Let's do 1,255. So first, what we're going to do is we're going to take this number, our first number, we're just going to modulo it by 2. So obviously, that's going to be a 1. Now, what is the division? Because we're going to need the division. So you want to keep track of the divide. That's the only thing is like this. As a human being, you're going to have to keep track of this. As when we get to the algorithm, obviously, we're just going to use a variable that we're going to keep modifying. So the computer is basically just going to, see it as the number itself changing, which is really what's happening. But it's just something that you got to remember to do as a human being. Whereas, the calculator or the computer will kind of just do that all at once, so to speak. So 1255 divided by 2. Whoops. So it's 627. And then we mod that by 2. Whoops. Holy moly. Sorry, guys. Brain fart. So that's going to equal 1. 627 divided by 2. 313. 313 divided by 2 is 156. Now we have a 0 here because there's no mod. 156 divided by 2, 78. 78 mod 2, that's also an even number, so it's going to be 0. Now, basically, all you're doing here is, like, mod 2, like, you can very quickly do this 0 or 1. The division is the part that's going to take you, like, mentally a second, or, a moment to type into a calculator, which is what I'm doing right now. However, this modulo is really easy. Like, I know this is going to be 1 because this is an odd number. Basically, all this means, and this is very useful to know, and, comp sci in general, is mod 2 equals 0 basically is equivalent to is even. Is even. That's very poorly kind of informally written there, but like if something by mod 2 equals 0, that means it's even. So if it's an odd number, it's going to be 1. So anywho, we're going to divide that by 2 again. We're going to get, I'm just going to go up this way. We're going to get 19. Mod that 2. That's going to equal 1. Mod that by 2. You get 9. And then you get 4 from that. And then from that you get 0. 2 mod 2. 0. And then there's a 1 there. So now we go backwards just like we did for the other one. So we get 1 0 0 1 1 right, now let's use our converter. Whoa, sorry. Converter to check. I just dropped my pen there. That's why I yelled out like that. So it was 1255. And let's just see how many bits this is. This is so the checks out 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So 11 bits. And our answer is 11 bits. Awesome. 100, 111. Yep. 00, 111. Correct. Okay. Awesome. This checks. So this method works. Now, that we know basically what our two different algorithms are, and obviously this one's way more efficient because, like I was saying, you know, this is literally just one repeated operation. No tables need to be made. No values have to be stored. Basically, you don't have to really do anything. You just repeat the same operation over and over again, and it just gives you the answers. It's a very, very convenient, very efficient algorithm. All right, so that being said, let's go over to our code and take a look what's going on over there. So let me all right, here we are in code land. So we have two modules. We have our modulo method and our powers method, and as you can see, even visually represented here, our powers method is more complex. It requires more logic to implement. Actually a lot more complex, 39 lines as opposed to 13. That's, almost exactly triple as, actually it is exactly triple as long. So that's kind of a nice little clean number that works out to, just by coincidence. Anywho, let's take a look at our powers method first, or not method, but module. So we have four functions here, sorry. So we have the conversion function, which is basically just like the driver function. It kind of just compiles the functionality of these three into one and ties them all up. Excuse me. Excuse me. And then we have our build table function, which is going to make that table of powers of 2, right? And fill it in with blank, basically zeros and ones. So, sorry, not zeros and ones. I just said that because I was looking at the initial value. And that's there because that's the first entry in the list. But basically the way that we're going to make this table is we're going to represent it as a list of lists. We don't use tuples here because tuples are immutable, and we wouldn't be able to change these, from 0 to a 1 to denote that, there is a 1 in that position. So we're going to use a list of lists. I hope that makes sense. Kind of a lot of words that I just mushed together there, but yeah, list of lists in order to represent a table. So while the power, really I should say, yeah, whatever. Power works. It's kind of confusing though because it sounds like the power that you're raising it to. This is not the power, but it's the power of 2, not the power itself. So it's not like 1, 2, 3, 4, so on. It's 1, 2, 4, 8, 16, 32, so on and so forth. So while that is less than the number input, we're going to double it and then append to the list, a new entry with 0 as a placeholder and then that given power. So basically what this is going to do is make a table all the way up to, the stopping point that we defined earlier, which is where the powers of 2 become greater than the number that we're trying to convert. Okay, so sorry, kind of motor mouthed my way through that, but I hope that made sense. And then we return the table. Now, to fill the table, we're going to take 2 arguments, the number to fill the table with, like to be converted basically, and the power table that we were given. The input, we're going to set the input into equal to the number just so that we have basically a value that we can modify without being destructive. And then the power table, we're going to reverse it because we want to go from the highest value of the highest power of 2 first. Then basically we're going to check if trying to think of the best way to verbalize this. Hold on, give me just 1 second. So basically what we're going to do is we're going to iterate through the power table, And then at every entry in the list, if the okay, what's the best way to phrase this? We're basically just doing the logic that we did on paper. We're going through each entry in the list and we're checking if the power of 2 is greater than the value that we're currently working with, like our working value that's being subtracted from. Okay, that's the best way to put that. And if it is, we put a 1 at that index in the power table. Okay, sorry, it took me a minute to get there. But yeah, that's what we're doing. Then we're going to subtract from the input that value because, we're taking away, just like we did on the, not paper, but, the simulated paper there. And then we're going to return the power table. And then table to string, very simple. We just go through every pair in the table, we grab the first index, and we, return it as a result. We just convert it to a string. Very, very straightforward and self-explanatory. So, actually, before we run the main, let's check the modulo. So yeah, this is like a little bit more complex. There's a list of lists going on, and you have to like go through their indices, which is why it kind of took me a second to try to think of the best way to verbalize what's being done here. Yeah, at the end of the day, it is literally the exact logic that we just like in the exact steps that we just took on that blackboard. But we're just doing it in terms of Python language, right? So next we have our modulo function, and this is just a cute little thing. Convert num. Same thing. We make our input, which is the going to be our working value, so that it can change and be divided and so forth. We make an empty result, and then while this is greater than 0, the result is we're going to add to it the modulo of 2, just like we did, and then we're going to add it to itself, and then we're going to divide the input by 2 so that we have the new value to work with, and we're just going to loop through this. So this is literally, again, the exact logic that we just did on the blackboard, but in 3 lines of code. It's extremely simple, and then we're just going to print the result and how many bits it is. Just I added this bit counter just because it is helpful for quickly checking your results, and also it was helpful for debugging because sometimes my modulo conversion was having like a different error than the other one, and they were getting different amounts of bits, so it was just helpful for debugging. So that's why I have that there. And then we return the result. Yeah, so that is the logic of these 2 modules. I think it's pretty simple and straightforward. And then our main py just imports them both. We make a take input function just so that it can perpetually, take new inputs. And then, it calls itself just so that whenever, it will infinitely loop basically until you terminate the terminal. I could make this more complex and have like an exit case and all that, but I don't think that's necessary for this project. Basically, it just asks for your number for the conversion, converts them both, and then repeats itself so you can compare. And I have had the convert functions. I added specifications of which is which, and the bit count, like I was saying a second ago. So let's say we want to do. Let's pick a small number to start. I'm just gonna hit 3 numbers randomly. Whoa. Fat fingered a few buttons there. All right, 658. Now it's printing in our convert, I have it print the table just for debugging purposes. I can actually get rid of that just because I wanted to be able to. So that's actually good. Before I get rid of that, this is a good way to visualize. Like this is the list of lists that we're building that represents our table, right? Where the first index in each list is the 0 or 1, and then the second is the power of 2, right? So yeah, anywho, that's how we did that, and yeah, the conversion works. They're both 10 bits. Let me just get rid of this print table line, and save, and then rerun, yada yada. 954. 10 bits. They're both the same. Let's use an online checker just to be extra sure. Binary converter. Decimal to binary converter. Okay, and our number is our number is 954 and 11, so 10 digits. 111 0 111 010. Yep, correct. Okay, awesome. Bingo. Now let's try a really big number. I'm just gonna mash buttons. Now computers are awesomely fast. Mine especially. I have a very nice computer, so obviously neither one of these methods took very long, but if you were trying to do this by hand, it would take you an absurd amount of time, probably to do both, but obviously orders of magnitude longer to do the powers of 2 result. But anywho, point is that we get the same result either way, and we can check it here. And that looks the same to me. 2 trailing zeros, 3. I mean, I can fully verify it, but that looks good. And I know that it works because there's no reason that it would randomly not work for some other number. I've tested it for, even numbers. I've tested for powers of 2 and all that, which we can try as well, 256. We'll give the correct as well as one below it and one above it. No weird issues there. So yeah, that's about it for this week. Hope that was a good, helpful video. Yeah, I think that this was kind of a good use of the little blackboard thing there. But yeah, I just wanted to make sure that I fully articulated what I wanted to get across. Anywho, that'll be all. I'll see you in 2 weeks for the roundtable on our final assignments. And yeah, it's been a great semester. I'll see you then, and I appreciate you watching. Thank you.